So I'm going to talk for the next half an hour or so about how particle accelerators and particle physics in general are used in conjunction with astronomy to understand the origin, evolution, and structures that we see in the universe. You've seen the Large Hadron Collider before, so I don't need to introduce that. But at first sight, it is not clear how doing particle physics, which you might think of as exploring the structure of matter, can have anything to say at all about the early universe and the processes that happened in the early universe, and perhaps even begin to allow us to understand what the universe is made of and how it has evolved and what its future might be. Just to give you some sense of the scale of the challenge, this is a visualization of data, real data, which is telling us about the structure of the universe as we see it today. It's called the Sloan Digital Sky Survey. So what you're seeing there is the distribution of galaxies in the sky, the measured distribution of galaxies. So, of course, these aren't real pictures of galaxies, but their positions are correct. So this is a fly-through of the local universe. I think it extends out to something like a third of the way to the edge of the visible universe, the observable horizon. And you see that there's a lot of it. Each point in this visualization is a galaxy, so perhaps 100 billion, 200, 300 billion stars like our sun. And you see that the galaxies are a snowstorm of galaxies, essentially. But they're not completely randomly distributed. They're distributed in rivers and clusters of galaxies. There are flows of galaxies. So this is the universe as we measure it to be today. And one of the great challenges in cosmology, a challenge that's been largely solved, actually, at least to some extent, is to understand where those structures came from. And to understand where those structures came from, you have to trace the history of the universe back in time as far as you can. I should say that the current estimate for the number of galaxies in the observable universe is around 350 billion large galaxies, so 350,000 million large galaxies. And we have extremely strong evidence that the universe extends way beyond the visible edge, so the edge of the universe that we can see that light has had time to travel to us from, if you like. So 350 billion galaxies, the universe may indeed be infinite in extent. We don't know. So that's the Sloan Digital Sky Survey. Just to show you one photograph before I carry on, because that was, as I said, a visualization of a data set. This is the deepest image of the universe that we've been able to take. It's an image from the Hubble Space Telescope. It's called the Hubble Extreme Deep Field Image. So it's an image of a piece of sky you would cover if you took let's say a 5p coin and held it around 20, 25 meters away or something like that. So a very small piece of sky, certainly significantly smaller than a full moon. It was a piece of sky that was chosen deliberately because it was relatively empty. So there were no particular bright galaxies or bright stars in that piece of sky, but the Hubble took a very long exposure photograph of that piece of sky over many, many months. And this is the current iteration of that photograph. And you see that it's full of structure. In fact, virtually every point of light in that photograph is a galaxy. There are over 10,000 in this image. And the most distant galaxies in this image are over 13,000 million light years away, 13 billion light years away. So in this image, there are images from almost the beginning of the formation of galaxies. So 10,000 galaxies in that image. So as I said, it's not obvious immediately how particle physics and particle accelerators can help us to understand how that came to be, how the structures came to be, and why they're distributed the way they are in the sky. The clue, though, is that the universe is not eternal. I think as you saw in a previous talk, and as you all, I suspect, know, the universe had I would say beginning for now, but at least there was a hot, dense phase around 13.8 billion years ago, which we can refer to as the Big Bang. I'll say why that's potentially a semantic thing to say a little bit later on when we discuss questions such as, well, what happened before that? Why did the universe get into a hot, dense state 13.8 billion years ago? But this is the sort of standard picture that you see drawn. So hot and dense 13.8 billion years ago, the universe has been expanding and cooling ever since. And the structures that we see today are properties of an old and cold universe. The point is, if you run time back from today, the universe, the observable universe, gets more and more compact, and therefore it gets hotter and hotter. And so particle physics comes into play when we ask questions such as what was the physics like way back towards the Big Bang when the universe was hotter, by which we mean high energies. So particle physics experiments and accelerators you can consider as laboratories that recreate the conditions that were present in the very early universe, so we can observe the physics that was present there. And it turns out, remarkably, that the physics is simple and understandable, and we have an extremely good grasp of it. And it's worth just pointing out, though, another thing I want to talk about is the balance between not only astronomy and particle physics, but between theory and experiment. And it's just worth, as an aside, noting that this idea that the universe had a beginning and a Big Bang was actually suggested theoretically before it was measured experimentally. It was suggested from this equation, which is Einstein's theory of general relativity, which is 100 years old this year. So just late 1915 was the first publication of general relativity. There's the equation. It's not particularly instructive. It might be to the physicists, not to the non-physicists perhaps. But it's quite a simple equation to understand. Essentially what it says is that given some distribution of matter and energy, that's what you plug into the right-hand side of that equation, then out comes, well, essentially the shape of space and time, the shape of space-time. So an example, the first application that Einstein put his theory of general relativity to, was to look at orbits in a solar system. So to work out what happens in a solar system, you'd plug in a spherical matter distribution on the right-hand side, which would be a star. And you'd ask the question, well, what do the paths look like, the straight lines, in Einstein's terminology, through that curved space-time? What do they look like? And the answer is, not surprisingly, they look like orbits. And one of the first predictions Einstein made with that equation was of the orbit of Mercury. And he came out with a prediction for the orbit which was more accurate than the prediction you get from Newton's laws. So that was the first thing Einstein did. But very shortly afterwards, Einstein did something which he actually wrote a letter to a friend of his and said that it was the sort of thing that he thought might get him confined to a madhouse because it was an audacious idea. The idea is that if you've got an equation that tells you with some matter distribution what the space and time look like, what's the story essentially told by that equation, and you can do it for a solar system, why can't you do it for the rest of the universe? And you might say, well, that's tricky. How would I work out the matter distribution for the universe? Well, Einstein did the simplest thing that he could, which was assume a completely uniform matter distribution. So it's a reasonable thing to do, the simplest thing you could do, the simplest model of a universe. And when Einstein and others did that, by the mid-1920s, they found that the story that's told by that equation is this story, essentially. You don't have a stable space-time. If you just consider what Einstein's theory predicts from a uniform matter distribution, it predicts a universe that is either expanding or contracting. And actually one of the first people to do that was a Belgian priest called Georges Lemaitre. And he was at a conference with Einstein in 1927, which is an important date. And he said to Einstein, I think your equation, your theory, predicts that there was a day without a yesterday. It predicts, because if you imagine that you've got a universe that isn't stable, predicted by the equations, it's expanding or contracting. Let's say it's expanding, that implies that it was smaller in the past, and therefore there was a moment when it was very small indeed, a point with a day without yesterday. And Einstein apparently said to him, your mathematics is excellent, but your physics is lousy. Because he didn't want, Einstein felt uncomfortable with the idea of a universe that had a beginning. He wanted a universe that was potentially eternal. And actually, I'm going to talk about it later. So if you look at the second term on the left-hand side, that's called the cosmological constant, now known as dark energy. And Einstein inserted that to try and produce a stable universe out of his equations. You're allowed to do it mathematically, but then took it out and called it the biggest mistake of his life. That's interesting because you get a prediction for the Big Bang from Lemaitre and others in 1927. It was 1929 when Hubble showed that distant galaxies are receding from us, and the further you look away from the Earth, the faster the rate of recession, the faster the rate of recession of the galaxies. This is an original plot, actually, in 1929, which pinned down experimentally the idea that the universe is expanding. But I think it's interesting, and just with relevance to something I'm going to say later on, to note that the expansion of the universe was a theoretical prediction, a consequence of Einstein's equations, before the experimental data came along. So that's the key link between particle physics and astronomy. The link is this. As you go back in time, you go to higher temperatures, the universe, or the observable piece of the universe, that's 350 billion galaxies in it today, is getting smaller, it's getting hotter, and so the physics is changing. And one of the jobs of the LHC, or the job of the LHC if you like, is to recreate those conditions so we can take photographs of it. Essentially a time machine. It's like taking a camera back in time to the early universe. How far back? You see it on this picture, that border there between something that says electroweak era and lepton era, around a billionth of a second after the Big Bang or so, those are the conditions that are recreated in the proton-proton collisions at the LHC, actually up to something like 600 million times a second. So bang, 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 little, not mini Big Bangs, but mini laboratories where you recreate those conditions. And the job of the particle detectors is to take the photographs of those collisions to observe the physics. So what is the physics there? Well, here it is. I'm going to show you another equation. This is an interesting equation. It's a triumph. It's probably one of the great triumphs of 20th century physics, along with Einstein's theory of general relativity. That's called the Standard Model Lagrangian. That summarizes or encapsulates everything we know about fundamental physics other than gravity, which is in Einstein's theory. So the three other forces of nature, the strong force and the weak forces that operate inside the atomic nucleus, and electromagnetism, all the properties of those forces are contained within that equation. It was written down based on physics, based on essentially two pillars, on relativity and quantum theory. It was written down in the 1970s, and you see by the 1980s it was making very precise predictions. Essentially what it allows you to do is link together observations of different particle collisions and make new predictions about physics that is at that time yet to be discovered. One of the interesting predictions there from 1981 are the masses of two particles called the W and Z particles. Now, what are they? Well, they carry one of the three fundamental subatomic forces, one of the four fundamental forces of nature, called the weak nuclear force. So the weak nuclear force will be familiar to the people who are doing A-levels here. It's the force that's responsible for radioactive beta decay. It's also the force that turns protons into neutrons inside the sun, so the sun can carry out nuclear fusion reactions. It's been known to be an interesting force for a long time, since the 1930s. It's odd because it's very short range. So you think about electromagnetism. Electromagnetism has an infinite range. Why? Well, in particle physics language, you would say because the particle that carries that force, the photon, has got no mass, so it can range across the universe. That's an interesting concept, as you just mentioned. The way that particle physicists think about forces is they're carried by other particles. So you picture two electrons with electric charge coming together. Why do they deflect off each other if they have the same electric charge? Because a photon or photons jump between those electrons and they carry the force, mediate the force. So electromagnetism is carried by photons. The strong nuclear force carried by gluons, which stick quarks together to make protons and neutrons inside the atomic nucleus. And then the weak force carried by these things, the W and Z particles. Now, that was interesting and odd, and it's an interesting prediction actually. It comes from measuring processes like electrons scattering off particles called neutrinos. So you can measure certain things and make a prediction for the mass of these things. The fact that they have mass means the weak force is short range. That's important because there are billions of neutrinos which only interact through the weak force, passing through your head every second from the sun. You don't feel them. I think it's about 60 billion per centimetre squared per second, actually, at the Earth's surface. So they're going through your head now. The reason you don't feel them is because they've got to go extremely close to an electron or an atomic nucleus to interact. Why? Because the particles that carry that force, the W and the Z, are massive. What's interesting from this point of view, from this prediction, is that that prediction was made within a framework that predicted something else, predicted the Higgs particle, which has been mentioned and I'm sure you've all heard of. How did it do that? Why did it do it? Well, very briefly, the idea in particular, I should say that those particles were discovered very shortly afterwards, actually, so we know they exist. We've made precision measurements of their masses, and they are, broadly speaking, within the range of those predictions that were made back in 1981 before they'd been discovered. So that in itself is a triumph. But interestingly, what happened, and the reason that that structure, that thing there, the standard model of particle physics is the way that it is that you can't just introduce masses by hand for those particles. If you do, you break the mathematical structure of the theory. You make it essentially meaningless. You mean that it can't make predictions. You break what are called symmetries of the theory. So the deep mathematical structure that led to that theory being written down in the first place prevents you from just sticking masses in, particularly for those force-carrying particles at random. So you have to do something else, a clever thing, and the clever thing is the bottom two lines of that equation there. It's called the Higgs mechanism. In a kind of early universe sense, then you can explain the Higgs mechanism like this. The picture is that before the energies that the LHC generates, so let's say before a billionth of a second after the Big Bang or so, the universe was in a hot state, and it was so hot that particles had no mass at all. And why do I say that? Well, the picture is that as the universe expanded and cooled, then something happened. What happened was that the lowest energy configuration of empty space was not for it to be empty. The universe went through something which you could call a phase transition. So you're familiar with a phase transition. You imagine a window on a cold winter's day, and you look at it, then you can see ice form. Where did the ice come from? Well, the ice came from water vapour in the air outside. The water vapour changed state. It changed from vapour to solid on the window because the window's cold. And in physics terms, the reason it did that is because those water molecules configuring themselves into ice crystals mean that they have a lower energy than the water crystals in the vapour. It's the reduction in temperature that allows them to do that and get into that lower energy state. In the same way, that theory says, as the universe expanded and cooled, something condensed out into empty space. And the thing that condensed out was the Higgs field, or Higgs particles, if you like. So the picture, sort of slightly hand-wavy, but not very hand-wavy, in fact, is that the universe today, and ever since that moment, is full of a condensate. It's rammed full. You can think of it as every cubic metre in this room being full of a Higgs field, or essentially you can think of it as being full of Higgs particles condensed out. And the way that theory works is that the other particles get their mass by interacting with those Higgs particles. And that's what's happening now. And by the way, there's something interesting about that theory, which is odd, that if you just calculate how much energy is taken in that condensate, how much energy is taken in binding all those Higgs particles together, if you like, it's something like the 1,000 times the sun's energy output. So it's the amount of energy the sun outputs in 1,000 years per cubic metre, if you naively calculate it, which is a bit odd. There's a lot of Higgs particles in the vacuum, you could say. Why they don't do something to the universe is one of the great unsolved questions in particle physics. In any case, that's what the theory says. So today there is such a thing as the Higgs field. The vacuum isn't empty, it's full of the Higgs field, and the other particles get their mass by interacting with it. That's a direct prediction. It's one of the best examples I know, as well as general relativity, of what the physicist Eugene Wigner called the unreasonable effectiveness of mathematics in the physical sciences. It's a mathematical prediction. It's a prediction that's based on preserving the mathematical structure of that theory with inputs from experiments over the past 100 years or so since the birth of particle physics, but it predicts the existence of this thing, the Higgs particle. And as you know, the Higgs particle has been discovered. And I just show this. It's a picture from the ATLAS experiment, which is an end-on picture. So this is a proton-proton collision, or actually many proton-proton collisions. The protons are coming in above your heads into the screen and from the other end, out of both rings of the LHC, if you like, colliding in the middle. And although you can't say for any particular collision that we're looking at Higgs particle, you have to do it probabilistically, it is likely, or at least possible, that you're looking at Higgs particle here. The interesting things are those four tracks. You heard mention of muons, I think, earlier, these heavy electrons that we're thinking now are building into the next generation of particle accelerators. That's 4 muons flying out, which is one of the predicted ways that Higgs particles can ultimately decay. So the Higgs particle has been discovered. You think about that, it's a triumph. I loved what Peter Higgs said, actually, when he was asked, essentially it's a theory that was put together in the 60s by Peter Higgs and many others. And you probably saw it when one of the reporters, they always ask you, how do you feel, Peter? that the biggest experiment ever built has now confirmed that your theory is right 50 years after you published the paper. And he said, it's very nice to be right sometimes. Which was a great piece of understatement. But there we are. So that's one sense in which particle physics helps us to address the early universe, recreating those conditions, and it's told us something very profound. Now, we don't know, I should underline, one of the reasons we want to continue our run in the LHC now, and we want the next generation of particle accelerators, linear accelerators, etc., is that what I said there about this, oh, well, the Higgs condenses out, and how did it exactly do that? We don't know the details of that. So it's not possible to be absolutely specific. We need precision measurements. We need to see how Higgs particles talk to each other. It's one of the key measurements we need to make at the LHC in order to disentangle that story. That story wasn't initially in the original papers that Peter Higgs wrote. It's what we now, the modern version of what's called spontaneous symmetry breaking and the way these Higgs particles condensed out into the vacuum. That's all physics to be explored. We now know that's broadly right, in the sense that we know there is such a thing as a Higgs particle and it's responsible for mass. But exactly how that works is one of the great goals of the next decade or future decades with the next generation of particle accelerators. So can we go back further than that? That's the experimental limit at the moment. As you've seen, perhaps you can see other processes in high-energy cosmic rays. But to go back in time further, how far do we need to go back to understand more than that? Well, we can go back, in fact, observationally. And you see there, if you look at this picture again, there's something which says afterglow light pattern, 375,000 years after the Big Bang. That's the cosmic microwave background radiation. And what is that, and what does it look like? Well, this is what it looks like, first of all. This is a picture of the sky. So it's the celestial sphere, if you like. So it's the sphere surrounding the Earth. And it's a picture of that light that was released 380,000 years after the Big Bang. The picture, again, is the same as the condensation of the Higgs particles in a sense. The universe was expanding and cooling, and after 380,000 years, it was hot enough for electrons to go into orbit around atomic nuclei. That meant that the universe became transparent for the first time. Before that time, it was a plasma. So there were charged nuclei, mainly hydrogen, helium, and a bit of lithium, and free electrons. And in that plasma state, photons can't journey through the universe very far. They keep scattering off the charged particles. So the universe is opaque. It's almost like one big star, in a sense. But 375,000 years after the Big Bang, that changes because the universe is cooling, the atoms form, becomes transparent, and that light can travel through the universe. And we can take a photograph of it. Here it is. What you're looking at there are very slight density fluctuations, in fact, in this baby picture of the universe. So you're looking at areas that are very slightly less dense than others. And you can immediately see that there's something interesting, just as I said about the patterns of the galaxies. These are randomly distributed, but they're not random. There's a characteristic size to them. There's not every possible distribution you can imagine. What we know now is that those density fluctuations are the seeds of the galaxies. And in fact, we can do computer simulations that take that data as input and then evolve the universe from that time and look at the distribution of galaxies that you get. And statistically speaking, it's the same as the distribution of galaxies we get today, which is a triumph of modern physics. So we understand that those density fluctuations in this photograph, which is real data, are the seeds of the galaxies. And we understand quite well now how those seeds transform themselves into the structure of galaxies that we saw in the Sloan Digital Sky Survey. But this can tell us a lot more than that. And this is where we get back to particle physics again. It can tell us a great deal, because what you're looking at here are, in fact, the way the universe behaved when it was 380,000 years old. You're looking at sound waves that rattled around, radiated through that plasma in the early universe, that were frozen in when the atoms formed and the light could travel through the universe. So you're looking at really the structure, the composition of the early universe. You're also looking at what's happened to that light ever since. So you're looking at the history of the evolution of the universe. You're looking at the expansion rate of the universe. You're looking at the shape of space, time, in fact, now. You're looking at the whole history of those photons, that they've journeyed through an expanding universe. It can all be disentangled. When you disentangle it, you get pictures like this. So this is a graph. I haven't got time to go into exactly. The idea is simple. The actual practice is quite complicated. But essentially, it's a mathematical description of that data, of that photograph. It's almost like a Fourier's decomposition, if you like. So if you have an MP3 player, you do Fourier compression on it. That's how MP3 players work. This is essentially a mathematical representation of that data. In fact, the dots on this graph are that data from that picture, which was taken by a satellite called Planck. So you see there's a tremendous amount of structure. As I said, these dots, although random, are not quite random. There are characteristic sizes, etc. These structures allow us to disentangle the composition of the universe and the history of the evolution of the universe. And you see that that green line on there is not a fit, actually. It's not a fit to the data. It's actually a prediction. It's a prediction given what we know about the composition of the universe and given what we know about Einstein's theory of general relativity and the way the universe has expanded and changed ever since. And you see that it's spectacularly good. It's a remarkable prediction. What goes into that prediction, or what goes in, is this. What goes in is that around 5% of the universe is made of the particles that we investigate in particle physics. So the stuff that makes up atoms and stars and galaxies, all the particles we've discovered. About 27% is in a form of almost certainly another kind of particle, which we call dark matter. You can't see it. It doesn't interact with light. It probably only interacts via the weak nuclear force. But you see there's about 5 times as much of it. It was first postulated, actually way back, I think in the 1930s. When you look at the way that galaxies rotate, you find out there's not enough visible stuff in those galaxies to hold them together. So you get a prediction that there's more stuff in there. You also see that there's something called dark energy, 70%. That was discovered because it was discovered that if you look out to more distant galaxies, you find that the rate of recession is increasing. So the universe is accelerating in its expansion. And it's been doing that for, I think, something like 6 billion years. So there's something else present which is driving an accelerated expansion of the universe. So as I say, you can put those into the models, or actually, conversely, you can fit the cosmic microwave background and read those out of the models. So what is this? Well, this is where particle physics could possibly help. I'm running out of time, but I just wanted to show you very quickly. This is not an advert for another book I'm writing, although these are plots that we're doing from the book. My friend Jeff Forshaw, my colleague at Manchester University, wrote a little computer program for a book we're writing about the early universe, which varied these things a little bit, and then just fits to the cosmic microwave background. So it's something you can do on about 2 pages of computer programs. So it's not, but putting known physics in. I just wanted to show you this because it's a little plot we made the other day where you see that if you vary the amount of dark matter, you get the red curve and the blue curve. And if you set everything to the defaults that we've measured, you get the black curve. So even with a very small, kind of almost noddy computer program, you can match this plot, the cosmic microwave background. I've got another one there where we vary the amount of ordinary matter. And you see, again, you change the position of the peaks, you change the relative heights of them. So they're incredibly sensitive to the constituents of the universe. You know, when you hear people go, and sometimes they say Big Bang's only a theory, you go, yeah, but it's a bloody good one, because look at this, it's fitting the data extremely well. So what about that stuff? What can particle physics tell us about that? Well, the dark matter, it may be able to tell us a lot. One of the best theories, and it was just mentioned very briefly, I think, in Graham's talk, one of the theories is that there is another family of particles, essentially a copy of the standard particles called supersymmetric particles. Again, there are good theoretical reasons for thinking that these particles exist. One of them, which you saw actually in the first talk, was that if you put those in, then the forces seem to come together and unify and come together in a very simple way at very high energies just after the Big Bang. If they exist, and if they do many of the jobs that they're supposed to do, which includes some of the theoretical stabilization of the mass of the Higgs, it's lighter than it should be naively, then those particles could be in reach of the LHC. We haven't seen any sign of them yet. That's been a surprise to some people because this was an extremely popular theory. And if they do exist, then they're a very strong candidate for dark matter. So that's one of the things that we would hope, if we had our fingers crossed, we would hope that we would see sign that those particles indeed do exist at the LHC in, hopefully, a few years' time. I just wanted to just make one last comment. It says I've got 12, I'm 12 seconds over. So in 12 seconds, I want to just say one more thing about cosmology. You might have thought, well, that's very good. We've got those little density fluctuations in the early universe. Where did they come from? They're very important. They seeded the distribution, the origin of the galaxies. Where did they come from? Let me just in 1 minute tell you the best theory we have to tell you where those little density fluctuations in the early universe came from. The best theory we have is called inflation, and it has in it a lot of particle physics. The picture is that before the Big Bang, when you define the Big Bang as the hot, dense phase that the universe was in 13.82 billion years ago, something else was happening. The thing that was happening was that the universe was undergoing an exponential expansion. So space-time was stretching much faster than the speed of light. It was driven, in these theories, by something called the inflaton field. So it's something possibly like dark energy today, only significantly more powerful, driving an exponential expansion. When you do particle physics with the known laws of quantum field theory that we know today in quantum mechanics, in that environment, you find that particle production is happening all the time. So in a space-time that's expanding faster than the speed of light, the space-time is glowing, essentially, with particle production in a mechanism that's similar, in fact, to Hawking radiation, the production of particles that on the event horizon of a black hole, which gets radiation from the black hole, very similar idea. Because that's quantum mechanical, though, you don't get a smooth glow. You get fluctuations, and you can calculate them. And you can calculate them from a time when the observable universe was 10 to the minus 26 meters across, which is a piece of space-time that's not only smaller than an atom and smaller than a nucleus, but actually smaller than the limit on the measurement of the size of an electron. So you trace a piece of space-time through that, through the Big Bang, when it was about a meter across, and through that, so the exponential expansion stops, the inflaton field decays, it dumps energy into space when the observable universe is about a meter across, and those fluctuations are frozen in, and you can measure them in there. When you do those calculations, you get precisely, statistically, that kind of distribution of random fluctuations. It's called a Gaussian random distribution. So our best theory of the universe suggests that there was a time before the Big Bang. It tells you what happened to heat the universe up to make the Big Bang, and it's based on a union between Einstein's theory of general relativity and what we know about particle physics. It's one of the great triumphs. And I haven't got time to tell you, because I'm 2 minutes over, that some of those theories also predict there may be an infinite number of universes. That's called an inflationary multiverse. But I'm not going to go any further because I've run out of time. So thank you very much.